Welcome to my channel Mugambe Brand 256. Today we are going to look at this example involving the relationship between the rate of heat flow and the latent heat, specifically the latent heat of vaporization. So an iron saucepan containing water which boils steadily at 100 degrees Celsius stands on a hot plate, and the heat is conducted through a base of a saucepan of area 4 square meters and uniform thickness of 2 exponent -3 meters. If the water evaporates at a rate of 0.09 kilograms per minute, calculate the temperature of the lower surface of the pan, given that the thermal conductivity of iron is 66 watts per meter per Kelvin, and specific latent heat of vaporization, which we are denoting as LV, is equal to 2.2 exponent 6 joules per kilogram. So this is the simple sketch that I tried to come up with. So here is our saucepan. So it is of thickness 2 exponent -3 meters, and then has its thermal conductivity denoted by Ks, meaning the thermal conductivity, the coefficient of thermal conductivity of this saucepan is 66 watts per meter per Kelvin, where it was placed on a hot plate until when water boiled at a rate of until when water evaporated at a rate of 0.09 kilograms per meter. Then to start with our first step, we have a relationship between the rate of heat flow Qt is equal to the mass rate, or the mass of water that evaporates off per second, times the specific latent heat of vaporization, which is LV. Well, so now in our first step we shall have to find this rate of heat flow. Reason being, we have the mass of the liquid that evaporates off per minute, but we are interested in the mass of the liquid that evaporates off per second. Well, so we have the mass, which is 0.09 but per minute, and every minute is equivalent to 60 seconds. So it is basically 1 minute times 60 seconds, where times the specific latent heat of vaporization, which is a constant that was given to us in the question, which is 2.2 exponent 6 joules per kilogram. So after substituting and doing the computations, it leaves us with a rate of heat flow which is 3,300 joules per second, or 3,300 watts. Okay, in our next step, applying the Fourier's law of heat flow, or the Fourier's law of conduction, which we had in our earlier lessons, that the rate of heat flow is basically the coefficient of thermal conductivity of a substance of the saucepan in this particular case, times the cross-sectional area times the temperature difference divided by the thickness of the substance that is in question in this particular case. So now, where we are having this heat being supplied, from the hot plate from the base of the saucepan, and therefore that means we shall be supplying more heat. That implies that the temperatures are very high compared to this other side where the water is boiling from. That's why in this step here, we are having that our temperature difference is going to be basically the higher temperatures that are being supplied from the hot plate minus the 100 degrees Celsius, because this saucepan at this point here, at that point there, it is in contact with water that is boiling at 100 degrees Celsius, and therefore it will have at the interface of water and this upper surface of the saucepan, we shall have the same temperatures, which are 100 degrees Celsius. That's why at this point here, we are substituting this 100 here, then divided by the thickness of the material, which is the saucepan, and we have it. So now, in the first step, we're able to get the rate of heat flow, which was 3,300 watts. So on the right hand side, we have the coefficient of thermal conductivity of the saucepan, which is 66, times the cross-sectional area of the saucepan, which was 4 square meters, multiplied by theta minus 100. So our point of interest is for us to find this theta here, which is the temperature at the bottom surface of the saucepan. Then divided by the thickness, which is 2 exponent negative 3, then cross multiplying either sides by 2 exponent negative 3 leaves us with 66 times 4 gives us 264 times the temperature difference inside here, and on the left hand side we have 3300 times 2 exponent negative 3 leaves us with 6.6, and then dividing either sides by 264 by 264, it leaves us with 0.025 is equal to the temperature difference, which is theta minus 100, and then adding either sides by 100 and then this other side by 100 leaves us with theta, which is this, the theta, then the 100 plus 0.025 gives us theta being equal to 100.025 degrees Celsius, and we are able to find the temperature at the bottom surface of the saucepan when it is placed on a hot plate, using the relationship between the rate of heat flow and the latent heat of vaporization. So we have been able to determine that temperature there. Thank you so much for viewing. We meet in the next tutorial.